This webcast continues the discussion of the problems in Worksheet 6B. So the previous webcast talked about number 1, and so let's go on to the second spring problem here. This spring is hanging from the ceiling. So up there in the ceiling, and then we've got a spring hanging down. And there is a block that has been attached to the end of it. I don't know the mass of it yet. It tells me that the spring constant is 3,220 newtons per meter. And it says that the spring was stretched 25 centimeters from equilibrium. So if this were equilibrium, where the end of the spring would have been if there was nothing attached to it, the spring was pulled downward, and so the displacement is negative 25 centimeters. Oh, and remember that we should probably work in units, so that's going to be negative 0.25 meters. Okay, so that's the picture here. It says that the block stays still. Those are important words. If the block is not moving, that means that the net force on the block is 0. Okay? And the situation here, there are just a few forces. There's the gravitational force on the block by the Earth. And there's the spring force that's pulling the block upward. Okay, there's no applied force or anything like that. We just have the weight of the block pulling down on the spring, and they are still. Neither one of them is moving right now. So the net force, I know it has to be 0. And looking at this force diagram, I know that I would calculate it as the spring force minus the gravitational force. So since spring minus gravitational equals 0, that means the spring force must be the same amount as the gravitational force. So let's see, if I calculated the spring force, that would be negative times the spring constant times the displacement, and the gravitational force would be the mass of the block times 9.8. Okay, so let's see here. They gave me a spring constant of 3220. The displacement was negative 0.25 meters. And therefore the mass, notice how these two negatives cancel here, right? That's okay, because really mass can never be negative, so that makes sense, is going to be 3220 times 0.25 divided by 9.8. Which is 82.143 kilograms. Okay, let's go on to number 3. So now we have a wooden cube. It's on a frictionless table, so we won't have to worry about friction. And it has 2 springs attached to it. There's one attached to the right, and there's one attached to the left. And of course both of those, then are, attached to a wall or something. The other ends are fixed. Okay, it's a 5 kilogram block. Okay, it says the spring on the left has a spring constant of 55 newtons per meter. And I'm going to call that spring 1. And I'll call the one on the right spring 2, just to make it simpler. The spring on the right has a K of 111 newtons per meter. Initially, both springs are in their equilibrium positions. But then the block gets moved toward the left by 10 centimeters. And when it does that, so the displacement is negative 10 centimeters, since I want to work in meters, that would be negative 0.1 meters, okay? When the block is moved to the left, spring 1 gets compressed, right? The first spring gets scrunched up, but the spring on the right gets stretched. So the block moving affects both of the springs. And we want to figure out the acceleration of the block when it gets released. Okay, so let's do a force diagram for the block. And we're going to think about it just at the point where it's released. So there's no applied force in our force diagram, right? So there's the weight of the block, and that would be its mass times 9.8, so that would be 49 newtons. And the table is supporting the block with a normal force, and that's also 49 newtons. Those two forces are balancing each other. Okay, we don't have any friction, but I have two spring forces. So first I'm going to take spring 1. That's the one on the left. It's getting compressed. And in order to go back to its equilibrium position, since it's getting pushed to the left, the spring force wants to counteract that, and so it pushes back to the right. So I'm going to have the first spring force is going to push to the right. And I can probably calculate that. It's negative k times the displacement, and so that would be negative 55 times negative 0.1. Okay, so my negatives cancel, and that confirms that I made a good decision to make this force point to the right. Okay, now let's talk about spring 2. It's getting stretched. When the block moves to the left, it stretches spring 2, and in order to go back to its equilibrium position, spring 2 needs to pull the block back toward the right. It wants to restore its initial position, and so that spring also pushes to the right. And I can calculate that. It would be negative the k, which is 111, times the delta x, which is negative 0.1. And so I get that the force from spring 2 is 11.1 newtons. Okay? And again, there is no friction in this particular problem. So my net force in the horizontal direction is just the sum of those two forces, right? The first spring force and the second spring force. And so that would be 5.5 plus 11.1. So that would be 16.6 newtons. And now that I know the net force, I can find the acceleration, which is the net force divided by the mass. 16.6 newtons divided by the 5 kilograms. Which would be 3.32 meters per second squared. And since it's positive, you know, just to say it again, this is to the right. Okay, and we have one more problem in the worksheet here. Number 4 talks about a mass on a frictionless horizontal surface. It's connected to a spring, and they're giving me the spring constant. Notice they're not telling me on what side of the block the spring is attached, but what it does tell me is that when the spring is released, it has a positive acceleration. That means that the acceleration is to the right. So if the acceleration is to the right, I know the net force must be to the right. So I'm thinking the spring force must be to the right. Okay? And since the spring force is always in the opposite direction of the displacement, well, the displacement of the spring must have been to the left. So it really doesn't matter whether I draw the spring on the right or on the left. I can still kind of figure out what I'm expecting. Uh-oh, I meant to lasso. Okay, so maybe I won't do a force, a picture here, and let's just see what we've got here. So it's on a frictionless horizontal surface, so I'm going to have just a gravitational force going down. That's going to be balanced by the normal force from the table, and then there's going to be a spring force pushing it to the right. Okay, so therefore I know that the net force, I have both the mass and the acceleration, so I can go straight to Newton's second law. Net force is mass times acceleration, so that's 20 kilograms multiplied by the 7.4 meters per second squared. So I can find the net force here. It's 148 newtons. Looking at my force diagram, the net force is just the spring force, because that's the only force in the horizontal direction. So therefore I know the spring force is 148 newtons. And the spring force, which is 148, is negative times the spring constant times the displacement. And so I'm trying to find the displacement. So 148 is going to be negative times 459 newtons per meter times the displacement. The displacement is 148 divided by negative 459. So it's going to be negative 0.322 meters. So when we solve this, we're getting a negative displacement, but that's what I had already inferred from the information that it was accelerating to the right.